Hello, warm welcome to the session. We are in the fifth lecture of this series on digital electronics. We are dealing with the chapter Boolean Algebra and K-maps. So let us move on to the next section where we discuss about the multiplexers. Okay, so coming to the GATE exam, a question will be 100% sure. On mux, the multiplexer question will be damn sure. You will get 1 mark or 2 mark questions from this particular section. So the question will be like this. So let me have so mx will be like this. Okay. So here there will be inputs. Let us take the inputs are I0, I1, I2, I3. This one set of input and the other set of inputs will be here. Let us take this as S1, S0. So, and there is a output here. Now I have three inputs, three Boolean variables P, Q, R. Among those, P is supplied here, 0 here, P dash here, and 1 here. So all these are data inputs. Okay, and Q is here and R is here. These are known as select lines. Okay, select lines. And now we'll get a function here, which is a function of the Boolean variables P, Q, R. So this is 4 inputs are there and 1 output is there. So this is known as 4:1 mux. Mux implies multiplexer. What a multiplexer does? Multiplexer solves or combines various inputs, data inputs, and gives a output. So this is a 4:1 mux. So what the question here? I need to find the function of PQR. So this is the question here. Now to solve this question, let us see what is a mux, what is a multiplexer, and all these details we are going to discuss now. Okay. So let us see the answer now. Now, what is a multiplexer? Multiplexer is a selection circuit. Okay, it is a selection circuit in which there will be many inputs. Out of that, we will select one output. We'll select one output. So this is a many to one circuit. Okay, let us see an example. So I have a multiplexer here. I have 4 inputs to this, and I have 2 select lines. So the down ones are known as select lines. So here the select lines are S1, S0, and inputs are I0, I1, I2, and I3. So this is a output function. Now, based on the 2 select inputs, Okay, if I want to if the select inputs are given as 0 0, what are the four combinations? 0 0 0 1 1 0 and 1 1. These are the only combinations. If the select line are 0 0, then we'll get f output as I naught. If it is 0 1, then I1, 1 0 I2, 1 1 I3. So like that, based on the select lines, we select the particular input and which will appear in the output. So what is the application of this multiplexer? So this is a shortcut for multiplexer. The first application is time division multiplexing. All our mobile phones uses time division multiple axis. Okay, this is the basis for that. So this is represented as TDM, time division multiplexing. And second application is the multiplexer is universal gate, can be used as the universal gate. That means any Boolean function can be realized using multiplexer. Okay, and third application is the field programmable gate arrays. It is known as FPGA. All our is DRDO missiles, Indian missiles, uses FPGAs, field programmable gate arrays. This use the multiplexers. So these are the applications of multiplexer. And now, how will a multiplexer circuit looks like? So let us see the multiplexer circuit. How will the multiplexer circuit looks like? So we know that there will be two select lines S0 and S1, and there are four inputs I0, I1, I2, I3. Now the multiplexer will have the combination of inputs like this. Okay, there is an AND gate. Okay, so this is known as AND gate with the two inputs and one output. Let me replicate this AND gate. Let me arrange the AND gate one below the other. Okay, these are the required AND gates for us. There are four AND gates. So let us see what are they are. Okay, so these are the inputs. So let us take the select inputs, that is S1, S0, S1, S0, S1, S0, and here last one S1, S0. Now If both S1 S0 are 0, then we'll represent it like this. Okay, then S1 is 0, S0 is the same 1, then S1 is 1 and S0 is 0, and both S1 are 1. So these are the select inputs. And if both, let us arrange I0 here. This is I0, this is I1, this is I2, and this is I3. And let us connect this to this to this, and let us connect the last one. Okay. So here, and finally, this all four outputs are connected to a single OR gate. This goes like this. This goes into this. Yes. Okay. So now in this circuit, based on the inputs, suppose what is the mux does when S1 is 0, S0 is 0, it should select I0. Let us test this circuit. Put S1 is equal to 0, S0 is equal to 0. Then what happens? This comes as 1 and this comes as 1. So S1 0. So one of the inputs here will be remain same. S0 will remain as 0. So this AND will get deactivated. Here S1 is 0. So this also deactivated. Both are 0. This also deactivated. Only this will be active. And when this is active, this supplies 1 here. And when 1 is supplied here, only I0 goes into the circuit. And this is an OR gate. As an OR gate, one of the input is I0. So F becomes I0. Okay. So that's how it works. So now F is, if S1 is equal to 0, S0 is equal to 0, F is I0. Now let us see one more new concept. Min term in two variables. So if there are two variables A and B, what are the possibilities? 0, 0, 0, 1, 1, 0, 1, 1. Okay. Min term M0 is represented as 0, 0, that is A bar B bar. M1 0, 1, that is A bar B. M2 1, 0, that is A B bar, and M3 is 1, 1, that is AB. Okay. Now the same above equation, if you see this diagram, then you can say that equation of multiplexer, that is mux, that is F is equal to, what can I write it as? I can write it as simply M0 into I0 plus M1 into I1 plus M2 into I2 plus M3 into I3. Okay. Suppose instead of S1 and S0 I have taken AB. Okay. Then immediately M0 implies what? A bar B bar, that is S1 bar S0 bar. Okay. Here it is given. See, this is S1 bar supplied to the AND gate, and this is S0 bar supplied to the AND gate. So M1 I1, M1 I, M0 I0 plus M1 I1 plus M2 I2 plus M3 I3. So 99% of the questions can be solved using this equation, the above equation. Okay. So if it is a 4:1 mux, let us go back here. So for this is a 4:1 mux. Like the equation that I have wrote before, this is a 4 is to 1 mux. What will be the function f here? So f here can be written as m naught I naught plus m1 I1 plus m2 I2 plus m3 I3. Similarly, if it's a 2 is to 1 mux, then how many select 2 is to 1 means there will be two inputs, right? I naught and I1, and there will be two select lines, S1 and S naught. Sorry. So for two inputs, there need not be two select lines. One select line is enough. Let us take only one select line, yes, because if S is equal to 0, I0 is selected. If S is equal to 1, I1 is selected. Okay. Now the output is, how can I write the F as? F is same M1 I naught, M naught I naught plus M1 I1. M naught is S dash and M1 is S. Okay. Same thing we can extrapolate to any number of mux. Suppose we have now dealt with 2 is to 1 mux over, 4 is to 1 mux is also over. Now let us take 8 is to 1 mux. So in an 8 is to 1 mux, what will be the inputs? Inputs will be I naught, I1, I2, so on up to I7, right? I naught, I1, I2. So this is a 8 is to 1 mux. So there will be 8 inputs and 1 output. I2, I3, I4, I5, I6, I7. And how many select lines will be there? So there will be three select lines, S2, S1 and S0. Why three select lines? Because there we require 3 bits to select 7 different inputs. Okay. So this is MSB, that is most significant bit, and this is LSB, that is least significant bit. And based on the select lines, we will have the output. So the output is F. That F is given as same M naught I naught plus M1 I1 plus so on plus M7 I7. So here we have represented the minterms. We represent the minterms in terms of the select lines S2, S1, S0. Is it clear? Now coming back to the given question. Yes, this is the given question. Let me take this question. Okay. Now, so data inputs are given, f of pqr is asked. So how can I do that? Now, just now we have studied f is given as, in this question, in the given question, m naught I naught plus m1 I1 plus m2 I2 plus m3 I3. Okay. Now, m naught is what? P. Sorry, m naught is represented as select lines, right? M naught is the select line q bar r bar, means q0 r0. 0 is represented as bars. Q bar r bar into I naught is what? You can see I naught is P here, plus M1 is what? 0, 1, that is Q bar R, and I1 is 0. Anything multiplied by 0 is 0. Then m2 into I2, 1 0, that is q r bar into I2 is p dash plus m3 I3, q r into I3 is what? 1. So that is p q bar r bar plus p bar q r bar plus q r. So this is the answer. If question is asked like in the given marks, what is the answer? What is the function f of pqr? And options are given. One of the option will be this. So I have to select the right answer. Okay. Now let us move on to the next question. This question has two multiplexers. Slowly we will increase the complexity. There are two multiplexers like this. And both are 2 is to 1 mux. 2 is to 1 mux means there will be two inputs and one output. So here one output is W. W is supplied as I naught and W is passed to the inverter. What an inverter will do? It will invert the bit. And there is one input here, S1. And this is connected to I naught and this naught is connected to I1. So this is a bit G. Okay, let us take this as function G. So this is F. This is S2. I need to find out what is F. That is the question. Now, to solve this kind of problems, we use a shortcut. See here, we already discussed what is that shortcut. So if I have a mux like this, it's a 2 is to 1 mux and I naught is here and I1 is here and S is here and function F is here. So function F can be directly written as M naught I naught plus M1 I1. That is as S select line is S dash I naught plus S into I1 is the function F. Let us take an example. Let us take a mux. This is an example. Let us have 0 and B here and 2 is to 1 mux. Let us have input select line as A here. What is the function? Function will be M naught I naught plus M1 I1. That is A bar into 0 plus A into B. A bar into 0 plus AB. So this will be AB. What is AB? AB is an AND gate. AND gate is represented like this. So this is A, this is B, the output is AB. Let us see one more example. There is a similar 2 is to 1 gate, 2 is to 1 mux. The first input is B, the second input is 1, and A is the select line. So if you select F, F is A bar B plus A into 1. This is A plus A bar B. That is A plus B. A plus B is an OR gate. A plus B is an OR gate. Okay. So now you have seen that using the same mux by changing the inputs and select line. In the first case you have got AND gate and the second case you have got OR gate. Let us see whether we can get inverter or not. Inverter means what? If you supply A, you should get A dash. If you supply 0, you should get 1. If you supply 1, you should get 0. Let us design an inverter like this. This is 1. Let us take this is 0 and select inputs as A. So this is also a 2 is to 1 mux. What is the function output? This will be M naught I naught plus M1 I1. M naught means A dash into 1 plus A into 0. So this is A dash. That means whatever a you supply, you are getting the final function as a dash. That means it is inverted. So you have realized an inverter. Okay. That means what? We can see that mux is used to construct AND gate, OR gate, NOT gate. Okay. We have constructed AND gate, OR gate as well as NOT gate also. Hence, mux is a universal gate. Is used as a universal gate to construct any gate. Okay. Now coming back to the given question. So this is the question given. Here what we need the function f. To find f, we have s2 and we need to know what is g. So to find g, let us write the output of this first mux. So what is g? G is s1 dash into w plus s1 into w dash. That is s1 XOR with w. That is g. Now coming to f. F is s2 dash into this connected to g. So s2 dash into g plus s2 into g dash. Okay, that is this is s2 XOR with g. If you don't know what is XOR, a XOR b is ab bar plus a bar b. This principle is this particular XOR gate is used here. So s2 XOR with g. What is g now? G is already here. S1 XOR with w. So this total function is s2 XOR with s1 XOR with w. So this is the answer. This is the answer for this question. What is f? Okay. Hope you are getting all these concepts well. Now, let us see what is FPGA. This is very important for the ISRO, DRDO, BARC interviews and exams. So let us see what is FPGA. FPGA is a programmable hardware. Okay. FPGA is a programmable hardware. This FPGA uses lookup tables. What is this lookup table? It is represented as LUT, lookup table. This LUT is nothing but mux, multiplexer. Whatever we have seen the multiplexer, that multiplexer is nothing but this lookup table. This lookup table is used in our FPGA. Let us see what is a lookup table. This lookup table, LUT, is used to realize any Boolean function. So now let us see the lookup table. So this is a mux. Mux will have 4 inputs, right? 1. So let us take this as 4 is to 1 mux. So 4 is to 1 mux has 4 inputs and 1 output. And how many select lines will be there? There will be 2 select lines. Let us take this as S1 and S0. Okay. Now for this mux, We add 4 SRAM, static RAMs. One here, second one here, third one here, and fourth one here. All the 4 are same only. They maybe I have written in different shapes, but 4 are same. So these are SRAM cells, static RAM cells, and the output is F. And the inputs are, let us say, I0, I1, I2, I3. What does a SRAM does? What does it do? SRAM stores one bit. SRAM stores one bit of data. Okay. So how is this SRAM cell combined with MUX? It is used to construct an AND gate. Okay. Let us see. So let us take this particular particular circuit. Now using this, what I need to do? I want to construct an AND gate using the lookup table. Okay. So there is the inputs. Let us take. I want to perform AND gate. That is A, B are the inputs, and I want to AND it and get A, B. Okay. So here, let us take the A, B, and the function F we need is like this. So the input consists of 0, 0, 0, 1, 1, 0, 1, 1, and the function F is 0, 0, 0, 1. Okay. Why? Because only when A and B are 1, then F becomes 1. Then let us take the select lines as A and B, and we can feed one bit in this SRAM cells because SRAM cell can store one bit. Let us store here 0, 0, 0, and 1. Okay. Now when we store 0, 0, 0, 1, what happens? Whenever what can I write F as? F can be written as 0 into A bar B bar plus A bar sorry A B bar into 0 plus A bar B into 0 plus AB into 1. All the multiplication with zeros will cancel out, which results in A into B. Okay. Thus, we realize the AND gate A into B. Okay. Got it? So we got the function F as A into B. And the same multiplexer combined with the SRAM cells. So this is nothing but lookup table. Okay. This is nothing but lookup table. Using the same lookup table, we construct OR gate. Let us see how we can do that. So same lookup table, using that we will construct OR gate. So let us take the same LUT lookup table. So this we have taken earlier. It is a MUX combined with SRAM cells. Now, what is the inputs? Inputs will be A and B. And what will be the output? Let us take the output function as CF. Let us take AB as 0, 0, 0, 1, 1, 0, and 1, 1. And function F is, what is the logic of A plus B, that is A or B? A or B is 0, 0, 0, 1, 1, 1. So whatever function is there, function values are there, we'll feed the same into our SRAM cells. 0, 1, 1, 1. And we will select S1, S0 as the inputs A and B. Now it's ready. See here. So this is A bar B bar into 0, that is cancelled out, plus A B bar plus A bar B plus AB. Okay. So what can I write it as? This and this you can take common. AB bar plus A bar B. If you take A common, it will be B plus B bar plus A bar B. So B plus B bar is, if it's 0, this one. If it's 1, this is 0. So either case, 0 plus 1 or 1 plus 0, this is 1. So we'll replace it by 1. So 1 into A is A. A plus A bar B is nothing but A plus B. So A plus A bar B is equal to A plus B. This is one of the theorems in Boolean algebra. So we finally got F as A plus B. Thus how we realize the OR gate using the same LUT. In the previous cases, what we have done using only the mux multiplexer, we have changed the inputs, we have changed the output. Thus, we have found what is AND gate, what is OR gate. But now what we are doing, we are not changing anything. We are just changing the SRAM cell content, and we are realizing different logic gates using the inputs A and B. Okay, let us see how to realize the XOR gate using LUT lookup table. And again, we do the same thing here. We'll take the inputs A and B and the function F. We apply the truth table. So the truth table is 0, 1, 1, 0 here. So whenever 1, 0 or 0, 1 occurs, then 1 is occurring. Then we supply the S1 as A and S0 as B, and we'll write the truth table of the function as here in the SRAM cells. We'll feed the SRAM cells like this. So this gives F. Simple. Like this, you can utilize the lookup table to realize any Boolean function. It's easy, right? Only one hardware arrangement you have. Using that one hardware arrangement, you can find any Boolean function by adjusting this SRAM cells. Okay. And inputs also you don't need to adjust because only two inputs are available, and directly you can find out the required function, Boolean function. Okay. Now we will see how to design. Sorry. So next we'll see. Next question is design 2-bit binary multiplier. Okay, design 2-bit binary multiplier. Let us see how we can do this. 2-bit binary multiplier means 2-bit means what? Size of each input is 2-bit. That is, let us take two inputs X and Y. One input is X1, X0. Second input is Y1, Y0. So let us take one example. Let us take X as 1, 1 and Y as 1, 0. 1, 1 corresponds to 3. In binary, 1, 1 represents 3. In binary, 1, 0 represents 2. If you multiply 3 by 2, we should get 6. Let us see how to do that. So how we will multiply 0 into 1 is 1. 0 into 1 is, sorry, 0 into 1 is 0. 0 into 1 is again 0. Then coming to 1 into 1 is 1. 1 into 1 is 1. So if we do that, we are getting 110. Yes, 110 corresponds to 6. Both are matching. So what we are normally doing here, we are multiplying the units place of first one with the each and every digit of this previous number, and we are writing it here, and we are doing the same thing for the second number also, and we are shifting it. First we are shifting the second product, and then we are adding this quantity with this quantity. So we are using shift and add technique. Okay, this shift and add technique, the writing a program for shift and add technique will be very, very important for the ESE examination. Okay, now you have similarly, we have taken an example, but actually we have two values, x1, x0, y1, y0. So when we have the two values, x1, x0, y1, y0, if you want to multiply them, then first thing what we will do, x0, y0, second one, x1, y0, then we will do the same thing for y1, x0, y1, x1, that is x0, y1, this is x1, y1. So we have first of all multiplied, then we have shifted this particular quantity by one digit, and then we are adding those. Okay, first one what we are doing, we are multiplying each bit, this bit with this bit as well as this bit with this bit, like we are like that we are multiplying. Now we are adding these two bits, right? We are adding this, we are directly writing this here, we are directly writing this here, and we are writing sum here. Okay, when we get a carry here, that carry will be added back to this, is it not? That carry is added to x1, y1, and we'll get a sum here and one more carry here. That means to do this operation, what we need a half adder, is it not? Here one half adder is required, here one more half adder is required to add these two things. Okay, when we have the half adder, then we can do this particular realization of the circuit. Now what is a half adder? Let us take a multiplexer. I have, is a 2:1 multiplexer, so I have two inputs, x0, y0, and so sorry, we are seeing half adder, right? So this is not a multiplexer, this is a half adder. For a half adder, we add one bit with another bit, and what will you get output of a half adder? So this is half adder, not multiplexer, this is a half adder. So half adder has two inputs, x0 and y0, and it will have two outputs. First one is sum and then carry. So this is known as sum and this is carry. So if you have x0, y0 and carry and sum here, okay. Now x0, y0 combinations can be 0, 0, 0, 1, 1, 0, 1, 1. So this is min term 1, min term 2, min term 3. Now 0 plus 0, the sum is 0 and the carry is also 0. 0 plus 1, sum is 1, carry is 0. 1 plus 0, same thing. And 1 plus 1, sum is 1, carry, sorry, here it is 0, 1, it is 0, 1. 1 plus 1, if you do, the sum is 1 and carry is also 1. Now, if you specifically see what is S0, only see S0 and don't see this one, C1 you neglect. So S0 here is 0, 1, 1. 1. Sorry, 1 plus 1 is 2, right? So we are getting sum as 0 and carry as 1. Yeah, if you see, carefully observe, for 0 0 we are getting 0, and for 1 1 we are getting 0. So S naught is XOR gate combining X naught XOR with Y naught. Okay, so this is the sum, and C1 is nothing but X naught into Y naught. So this is M3. Now what does this mux should be made of? So I have X naught and Y naught as inputs, and similarly see here S1 and C1, S naught and C1 as outputs. So for these two inputs X naught, Y naught, if I want to get S naught, what I have to do? I have to do XOR of X naught and Y naught. And for carry X AND of, so AND gate here, this is S naught, sorry, X naught and Y naught. So this should be the circuit. Yes or no? So this is how we design a half adder. Nowadays, all microprocessor, microcomputers, microcontrollers, DSP, microcontrollers, microprocessors, DSP means digital signal processors. All these have multiplexers. Okay. Now coming back to the question, we have designed what is a half adder. Now what we require? So we have to add, we require one half adder here and second half adder here. So we have to design 2-bit binary multiplier. Okay, we need to design 2-bit binary multiplier. And from the previous discussion, we have seen that this is the 2-bit binary multiplication in mathematical form. Here there are two inputs, x1 x1 y1 x naught y naught. Okay, so two inputs are there. Now what we have to do with two inputs, we have to make them multiply, which is done by the carry function of the logic circuit, and we have to add them using a half adder. So there are two half adders required here. So if you want to use a circuit, let us try to manifest it. There is an AND gate. The inputs of this AND gate, let us say this is x1 y1. Let us take 4 AND gates. So this has x0 y1. So where is x0 y1? It is here. Then x1 y1 is over, is here. Next one is x1 y0. x1 y0 is here, and x0 y0. x0 y0 is here. Now what we are going to do, we will add x1 y0 plus x0 y1. x1 y0 plus x0 y1. Okay. We supply it to what? A half adder. So this is a HA. HA means half adder. Okay. So x0 into y0 is directly brought here. Okay. So x0 into y0 is directly brought here. Then x1 y0 plus x0 y1, x1 y0 plus x0 y1 are the inputs here as well as here. We will supply it to a half adder, and some of the half adder sum is replaced here. So this is also over, and carry whatever is coming here. So because half adder also has a carry circuit, right? That carry is added to x1 into y1. So x1 y1 is here. We have one more half adder here. So one input is this, and second input is this, and some you write it as s2. Yeah. And carry we write it here. Sum is s2 and carry is here. So the same thing we have represented in this mathematical form, that we have realized using the logic gates. How many devices are needed? 4 AND gates and 2 half adders are required. Okay. So thus using the two bit binaries, that is x1 y1 and x0 y0, by inputting them here, we have found out what is the output of the. So this whole circuit, let me construct a box here. So we need not know what is there inside the orange box. That is the circuit for a 2-bit binary multiplier, that is made of 2 half adders and 4 AND gates. But the output is coming here. So this is 1 bit, this is the second one, this is the third one, and this is the carry. So C S2 yes, and this we can taken it as S0. So this we take it as 1. This is the output. That means 2-bit binary multiplier output is C S2 S1 S0. Okay. That means if we check, if we multiply 2-bit numbers, we get a 4-bit number. That means how many bits are there here? 4, right? But we have supplied only two 2-bit numbers. Let us check that. Let us take an example. Let us multiply 3 into 3. What is 3 represented in binary form? It is represented as 1 1, and 3 is represented as 1 1, and 3 into 3 is 9. How 9 is represented in binary form? It is represented as 1 0 0 1. That means using 4 bits. So we have supplied 2 bits here and 2 bits here, and we got 4 bits here. Okay, so this is verified. 4 bits we are getting, that is verified. So that's how we solve this particular question. It's completed now. Now finally in this session, let us see what is full adder, because we have seen half adder. It will be easier now to see what is a full adder. Full adder means we'll have 3 inputs. Previously we have only 2 inputs, x and y. Now we have 3 inputs. So x, y, z, and we'll have a sum and a carry. We have x, y, z, that is 3 inputs, and we have sum and a carry. So the carry is given as xy plus yz plus xz, and the sum is given as x xor y xor z. How will we get this? We'll get this by solving the K map. Okay. So what is that K map? Let us see now. So we have the inputs X, Y, Z, and the outputs as one is carry, other one is sum. Okay. Now, when we have the inputs, let us take from the starting 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Okay. Corresponding. So these are the possible things, possible minterms M naught, M1, M2, M3, M4, M5, M6, and finally M7. Corresponding to each and every one of them, we get the sum and carry. Okay, sum is given as AX or BX or C. Okay, that is X XOR Y XOR Z. So this will we get it as 0 because 0 XOR with 0 is 0, and 0 XOR again with 0 is Z is 0. 0 XOR 0 is 0, 0 XOR 1 is 1. So similarly, this is also 1, this is 0, and this is 1. This is 0, this is 0, and this is 1. Similarly, carry, if you take carry is xy plus yz plus xz. So this will be 0, 0, 0, 1, 0, 1, 1, 1. Okay. So using the K map, if you try to reduce S and if you try to reduce C. So how we have done this? So we want full adder, right? That means actually we are doing 0 plus 0 plus 0. Which sum is 0, carry is 0. 0 plus 0 plus 1, sum is 1, carry is 0. Similarly, this also remains same. 0 plus 1 plus 1. This is sum is yes 0, carry 1. Up to here it is the output of a half adder. If you take the half adder and you neglect x here because x is always 0 here in these four cases, this is the replication of half adder. Now coming here, 1 0 0. 1 0 0 means let us take 1 0 0. What is the output? 0 and 1. So 0 and 1 is coming back here. 1 0 1. 1 0 1 is, sorry, not this one. 1 0 1 is same as this. Output is 1 0. So we get 1 0 here. Similarly, the other two also you can write. And once we wrote this, we minimize it using K map and you got the expressions. S is equal to this and C is equal to this. Okay. So here we end this session. We have learnt today what is a multiplexer, how to realize various Boolean functions using mux. Then we have learnt what is a FPGA, what is lookup table. Then we have seen what is half adder, then full adder. So that's what we have learnt today. Hope you have understood it well. So we'll stop it here.